So welcome back. We are going to talk about classical test theory. All right, so now that we have a definition of reliability with some examples of inconsistencies that can impact test scores, we need to establish a framework for how to estimate reliability based on changes or variability that occur in a set of test scores. So just a reminder from your intro stat classes that statistics allow us to make inferences based on changes we observe in our test scores to what we assume to be the underlying causes of those changes, the construct. So reliability is based on and estimated within a simple measurement model that decomposes any observed test score into two pieces. So X is our test score here, into true score and error. And T is true score, E is error. So that equation means that any test score is a composite that consists of two pieces. The true score is the construct we are intending to measure. We assume that T, our true score, is impacting our observation of X, our actual test performance. So the error score, in theory, is everything randomly unrelated to our construct that we're intending to measure. Yet, just as a reminder, and to reiterate how important this is, that error also directly impacts our observation, our measure, our test performance. Okay, so to understand that very straightforward model, we have to be able to ask the following questions. An observed score X, our test, vary across multiple repeated administrations of a test. If you took a test every day for the next year and somehow you forgot all about each and every one of those previous administrations, think like 51st dates or something, would you observe your score change? Or not you specifically, would your observed score change from one test to the next? And if so, why? And how could it change? Would it change? So there are two really important key assumptions to this question that classical test theory makes about the variability and covariability of T and E. So first, your true underlying ability T is assumed to be constant for any individual. So if your true ability can be expressed, say, as like 25 out of 30 points, each time you take a test, your true score will consistently be 25. It won't change according to classical test theory. So that's one. So two errors that influence an observed score at a given administration are assumed to be completely random and thus unrelated to your true score and any other error score from another administration. So at one administration of the test, some form of error is going to occur. And that could cause your score performance to decrease by 2 points. Maybe you weren't feeling well that day, or there was a pandemic, or you were unfamiliar with the test structure, even though your instructor gave you very specific empty versions of the test to give you that. So there are lots of things. So in this case, even though our true score was 25, what would be the error in that equation? And what is X? So I will leave that as an exercise to you, because you should be able to do that for the test. Is this subtle enough? All right. So, if we solve for E in this equation, that kind of clarifies that random error simply is the difference between our true score and our observed score. So a negative error indicates that our test score is too low, so it's biased downwards. And a positive error would indicate that X is too high. So, say for example, say a code produces an error of -2, and your X performance is now at 18. Compare that to your true score of 20. Versus guessing correctly produces an error of audience participation. I can't hear you. Sorry, I gotta entertain myself. Guessing produces an error of +3, which results in a test performance score of 23. Now, so for the math folks in the audience, let's break this down a little more. So based on the expected values of each component of a true score for each person, so we can see that our expected value of X is true score versus error, which we already solved for, which is E minus true score. Illustrates. Sorry, I got a cat in the background. So, as I've just broken down here, I encourage you to be able to work through this and think about the implications of this model. So, if we take the expected value of the difference between our true score and test performance, we can essentially see that if we assume error to be random, on average it is 0, which means that the difference between our true score and our expected value is 0. But that is on the average, and that is theoretical and done not at the individual level, but in the aggregate, where E and X are random variables, but T is an actual constant. That's your true score. So if we assume that people are randomly selected, then T becomes a random variable as well. And then we get that X equals T plus E. So therefore, in classical test theory, we can assume that error is normally distributed, which is a really nice property, is uncorrelated with true score, and has a mean of 0. It's pretty nice. All right. So, according to classical test theory, over infinite administrations of a test, assuming there's no practice effects whatsoever, your true score is always going to be the same. And error scores will vary completely randomly, some positive and some negative. But on the average, they're 0. So given these assumptions, what should your average observed score be across infinite observations? And what should the standard deviation of your observed score be over that infinite number of observed scores? So as you think through these questions and respond, you don't have to identify specific values, but you should instead think about means and standard deviations you'd expect T and E to have. Remember that X is entirely a function of T and E. So we can derive the properties of its composite from those two components. So I've provided a simulation here that either I will have embedded the animation or I will direct you to our code for you to look at. So here what I'm going to do is simulate a constant true score with randomly varying error scores from a population. Here the mean is 0 and the standard deviation is 1. Now in my code I set the seed to give R a starting point to generate our random numbers so that we can get the same results across different computers. So you should check out the mean and standard deviation of E and X. And I encourage you to create a histogram. Like right now. Cool. So, I think I'm probably just going to direct you to look at the R code for this. All right, so here's the explanation to that big question that I posed. So we know that our average observed score should be and would be your true score. Error, because it varies randomly, should cancel itself out in the long run. And your mean X score would simply be T. So the standard deviation of these infinite observed scores of x would then be, you guessed it, entirely due to error, since the truth doesn't change and any change in observed scores must be attributable to the error variability. Now, this standard deviation is referred to as the standard error of measurement, which unfortunately has an acronym called SEM. We're just going to discuss this more, but the reason I say unfortunately is that SEM is also an abbreviation for structure equation modeling, which, while we're not going to use in this class, we are going to use its baby sister, factor analysis, which is just baby SEM, structure equation modeling, not standard error of measurement. All right, but anyway, although it's theoretically impossible to obtain the actual standard error of measurement, since you can never have a test run an infinite number of times, we can still estimate our standard error of measurement using data from a sample of test takers. And as we will see shortly, reliability will then be estimatable as the opposite of measurement error. Cool. So this figure presents the three key pieces of the classical test theory model using PISA data. So we're going to be looking at total reading score from students in Belgium, because I felt like using Belgium. Total reading score is on the x-axis, it represents x, and the simulated t-scores are on the y-axis. So these total scores are calculated as t equals x minus e. This solid line here represents what we'd expect if there was no error, which in the case would be x equals t. So as a result, any horizontal scatter in the plot represents error. So note that true scores here are simulated to be continuous and range from 0 to 11, versus our x score, so our test score, are discrete. But I've jittered them here, so that's like staggering the points left and right to reveal the density of the points in this plot, so that you can actually get a sense of what's going on rather than having the dots stacked on each other, which you won't be able to see. So consider this. So for an individual with a true score of 6, the perfect test would measure true scores perfectly and produce observed scores of x equals t, which equals 6 on that solid line. In reality, a lot of people scored at or around t equals 6, but their actual score on x varied widely from 3 to 9. Again, any horizontal distance from the blue line for a given true score represents x. Cool. That's the idea. So that's wrapping up classical test theory. The key components of true score, error, and total score. Know them. They are important. Know them. Hopefully that was subtle enough. Cool.